We record the lectures, so in case you cannot come to each lecture because we have some overlap, then the video recordings will be made available in the L2P room. So let's start first with some organizational stuff. So the lecture is 3 hours lecture and 1 hour's exercise. Probably you already know the times. I'm very happy that both lectures are here in this room. It is very hard to move the lecture times because the lecture rooms are booked out. So if you have some complaints about the lecture times, we can talk about it, but it is very, very complicated to move. So also that's why the video recordings that in case you cannot always join, then you still have the possibility to follow the lecture. Now it is fixed, so the lecture is in English. And in order to follow the lecture, we have of course, some documents, the lecture slides and the video recordings, the exercises, some additional papers, and also the discussion room in L2P. You have only access if you register. So please do it if you would like to follow the lecture. And we will also develop a lecture notes during this semester. So you will get it also in the L2P room chapter-wise, always for the last topic that we had in the lecture. The exercise is in the 2nd hour on Thursday and will be held by the assistants. They are not here. My group is located in the main building in the room 2U27229. You can look it up in the internet. So if you have some issues, some questions, contact the assistants either per email or just drop by and check if they have time. Then if they don't have time, they can give you some appointments. And of course, also in the exercises, they are there to deepen the lecture concepts, but also to ask questions. It is really important. You will never have this support in your life again, like during your studies, that the people are just there for your education. So please, if you don't understand something, ask. Also in the lecture, I'm really happy if some questions come back or feedback, what you understood, what you didn't understood, and there are no stupid questions. So if I don't get any feedback, then I do not know, do I go too fast or too slow? Did I explain it in an understandable way or not? So please give me feedback. And I also ask questions that it is not so boring, just listening to me 1.5 hours. And these questions are really meant that you answer them. This way, it is much better if you communicate instead of a kind of frontal lecture. And by these questions, I can see if you understood what I told you, if I can continue or if I should stay a bit longer. Then there will be also an exam, of course, at the end of the semester. And if the exam, whether the exam will be oral or written depends on the number of registrations. We said up to 30 registrations, we will make an oral exam, and above, we will make a written exam. If we make an oral exam, then we will assure that there will be some dates which fit for you. So we will offer enough dates where you can doodle on which dates you are available. So in case you want to make the exam, it is assured that you will have a date which also fits for you. For the written exams, we will try to find one day, of course, where everybody can come. The exercises, as always, are weekly. So you will get them on Thursday, and you should hand in on next Thursday. We did not make it as an entrance requirement because I know that during your studies you have a lot to do. So we did not want to push you to do them, but they are, of course, very important. So it is really important if you don't have time, if you don't have time to make them written, at least look at them and think about them. Because if you push all these things to the end of the semester where the exam comes, then you don't get from this lecture what you optimally would get. I even don't talk about your exam result. I talk about what you take with you for your future work from this lecture. And for that, the exercises are very important. And I hope that they are also fun to make, so it is not only a due. So do you have any questions to this organizational stuff? If you have some questions during the semester, then just ask. Okay, what I would like to do today, this Thursday we will have 2 hours lecture because there is no exercise sheet yet. And for that next week we will have 2 hours exercise. First, solving the exercise that you will get this week on Thursday, and perhaps some additional stuff which is related to the lecture. So, and what I would like to do today is no real formalism, but just the motivation. So why do we need this lecture and which contents will we do this semester? Hello. Perhaps you can get some chairs from the room beside if you would like to sit. So satisfiability checking. You are here, so perhaps you already have some ideas. What is it about? I'm pretty sure that during your studies you already learned something which was related to satisfiability checking. So what do we do in? What do we check for satisfiability? You do not need to just tell if you have some ideas about it. Yeah, actually it is not so easy if you ask something that sounds like trivial and you would should formalize. So first of all, what do we check for satisfiability? Or what is satisfiability? What do we want to satisfy? Formulas. Okay, so it is about formulas. And what is a formula? Words could be also a formula. Depends on the... So how can I determine if something is a formula or not? Yeah, if I write something like this, is it a formula? Who is the opinion that this is a formula? And who is not? So we still have a lot of don't knows. You know, in Sparta you had to have an opinion, otherwise you was verbannt. I do not know the English word. And if I write something like this at the end, is it a formula or not? Yeah? Yeah, the answer is it could be, and it depends on the grammar, and the grammar defines the syntax of a logic. So we have the word logic. Formulas are defined by logic. So the syntax of the logic determines what is the formula and what not. And if I have a formula, it still does not have a meaning. So we will assign a kind of meaning that a formula is either true or false if it is a question which you can answer by yes or no, or if it is satisfiable in general. If you have variables in this formula, like x larger than 1, then this formula is satisfiable, for example, for the reals, because there is a real number, such that if I assign this value to this variable, then what you become at the end is true in real arithmetic. And if 1 is larger than 0 is 2, it is also defined by some further things which we will look later. So now if we come back to the questions, what is satisfiability checking? Then this is the question if formulas in a given logic are satisfiable or not, or with other questions, are they valid, always true or not? And what we want to do in this lecture is to develop algorithms and tools. So we do not develop tools, but we will look at tools which can answer this question automatically. So the satisfiability is the question whether there exists an assignment making my formula satisfiable, and validity is the question if this always holds, this formula always holds. That means if it is a tautology, and the two questions are a kind of equivalent. So if I can solve one of them, I can also solve the other one. So now we will come to these algorithms during the semester, but perhaps we start first with logic. What is a logic? And today we will go a short historical overview, how we came to that, what you learned today in computer science. And today we will not deal about the algorithms first. So logic. We already collected some ideas what the logic is, but perhaps we can make it a bit more precise. So what is a logic? Also in everyday life, I can say your argumentation is logical, or it is not logical. If we talk to each other and you try to convince me about some facts, and at the end you argued and I can tell, okay, I believe you or I don't believe you. What do I do if I come to this conclusion, that what you say is right or wrong? Exactly, some rules. And some rules, this I use for deducing some truth. So in general, logic is the study of the principles of valid inference and correct reasoning. So inference is this kind of deduction. Yeah, I have some facts. I assume them to hold, so kind of axioms. And then I have some rules, as you say, which tell me what I can infer from facts. And logic is very old, since the human beings are thinking, try to argue, and try to convince each other. And till the way of logic we have today, it is a long way. But before we come to that, so if the logic of the study of the principle of valid inference, then we also have to, we also make use of it, in which sciences play logic an important role, for example. Of course, in many, but typically. Which sciences are typical for using logical inference systems? Philosophy, computer science, and the last typical one, which you already got known to from the ground school on, primary school, mathematics. So these are the three typical areas. But of course, there are also, actually in each science you use logics. But formal logics are studied in these three mainly. And now let us come to the question, what is a logical system? We already had the syntax. So what we have is, we must say how formulas are built up. So how can I build logical statements? And then if I have some, then I can infer facts from axioms by inference rules. So for each formula, I can try to derive its meaning. What do I need to derive the value of a logical sentence, the meaning? So now I have some syntax, and I have an axiomatic system. If I write down now a formula, let us come back to A and B. Let's say it is proposition logic, so my syntax allows it to build. Let's say a formula is built up by either a proposition or the conjunction of two or the negation. Yeah, this is something very restricted. And then in this syntax, abstract syntax, I can build up this formula if A and B are propositions. And now I would like to know what is the meaning of this formula. What does it mean, A and B? Is it true?
So we need domains at which the variables are bound to.
Exactly. This leads us already to first order logic we will handle later. We need domains for the variables to have values for them. And then, so now I know what A and B can be. Assume they are Booleans. So they can have the value true or false. So what is the meaning of A and B? What is the value of A? If I know the value of A and I know the value of B, then I can use, let's say I have some inference systems, yeah? I have a rule telling me that if A holds and B holds, then also A and B holds. But it assumes that A and B holds. So I can evaluate this formula, A and B, only in the context of evaluation. I need a model for my formula. I need a model which actually gives values to my variables, functions, meaning to the functions, and so on. Every atomic part in my formula becomes now a value. And then I can take my inference system, my rules, to derive the meaning of formulas. And if the formulas do not have any free variables, then we call them sentences. Okay. And now assume I have a logical system. I defined first the abstract syntax, I defined some axioms, and I defined some inference rules. And now I can try to give meaning to the sentences, and I can derive some facts from the facts which I assumed. And these logical systems must have some important properties that in order to make use of them. Not all logical systems are useful. So what are the main properties of logics which you expect from them? Such that if they do not fulfill this, then you are sure it is for nothing good. For example, if I would like to convince you about one fact, and I argue, and you tell me, okay, you are right. And now I go to another person and I argue about the negation of this fact. I can also argue, and I convince the other person also, and this person says also you are right. So I got two answers from two different people which kind of contradict to each other. And if I have this in the logic, then yeah, you can derive thing, but you can also derive the opposite. Then it is mathematically, it does not make much sense. So this is something we would like to exclude. If I have a logical system, then I want that this is, let's say, free of contradictions. And other properties are connected to the evaluation of formulas. So if I have a formula, and I would like to derive its truth values, I have some axioms and some rules which I can use to derive it. What can happen? Is it the case that I can always derive it? Now let's say I would like to, again, A and B. I have a rule that tells me if A holds and if B holds. I just put it in context. I take an evaluation. Sigma is a model for A and sigma is a model for B. Then sigma is also a model for A or B. Now I allow also this junction. I can express it with the negation and conjunction. Okay, and now I would like to derive the fact that I add quantifiers all propositions A, it holds that either A or not A is valid. And I have one rule. So what is the meaning of this? Can I derive this meaning? The meaning of this formula? Given some... No. I cannot. Why? Because my system is not complete. Yeah? That means I can derive some truth or some satisfaction, but I cannot derive everything. It is not complete. Actually, this is not, it is painful, but it is not so critical that with these systems you cannot do anything. You have also logics. Probably you also know the halting problem. So the semantics of programs is, the termination of programs is not decidable. So if the question is not decidable, then can it be that I derive an axiomatic system from which I can derive the truth value of each statement, of each formula? Of course not. Yeah? Otherwise it would not be undecidable. Otherwise I could give an algorithm with which I can do that. So incompleteness is, it of course comes with undecidability. Of course if I have a decidable logic, then I would like to have also a complete system. But what is much worse is if I can derive something which I did not mean. And this is soundness. That means even if my logic is undecidable or if my axiomatic system is incomplete, what I want to have is soundness. If I derive something, then this fact is indeed true. So the three properties are consistency. I cannot derive truth and true and false value for the same formula. Then soundness, this is also a strong requirement. If I derive something, then this should hold. And the last property is completeness. If my logic is decidable, then I would like to have a system in which I can derive a truth value for each formula in this logic. Okay, now we did not fix the logic. We also do not do it now. At the end of the lecture, I will give you a short table which logic we will deal with in this semester. But what we do today is a short historical view. So how did they come to this logic? For example, to propositional logic, or did you get known to any other logics in computer science? Probably yes. What do you know besides propositional logic? Temporal logics. How many of you listen to model checking? Yeah, you all should know temporal logic. This is about arguing of passes of transition systems. Actually, computations of programs, for example. Other logics? You listen to math lectures. Yeah? What do you do there? First order logic, this is actually the very big picture. In first order logic, you have a kind of skeleton, and so black boxes, these are theories which you can plug in. So if you plug in different theories, then you get different logics. And now we come back to math. Exactly, in math you make first order logic, there's restrictions because you have numbers there, and you define operations on these numbers. And what you perhaps never thought of, but there is an axiomatic system behind. Yeah, you argue. You say, for example, if x is larger than 0 and y is larger than 0, then x times y is also larger than 0 in the real, let's say, real arithmetic. And you do this because you've learned it in school. But this is, of course, based on an axiomatization of the real numbers and an axiomatization of real arithmetic. So also there you have axioms and rules how to derive things. And one of the rules is this property of multiplication. So you make use of this rule. But till this point where we formalized first pseudo logic or temporal logic, this was a long way. This started at an informal way, and then till today it got formalized. So the informal way started very early. And we are around about 500 before Christi. And we say philosophical logic till the 19th century. And with philosophical logic, we mean that people try to understand the argumentation, this inference structure of the language, of the natural language. And this we look at first. So where did it start, and what was the problem with this natural language argumentation, which is informal? And if I say formal, then I always mean mathematical, with formal syntax and semantics. So the logic deals with sentences in the natural language, the philosophical logic used by humans. One example is if you say, all men are mortal, sterblich, Socrates is a man, therefore Socrates is mortal. So if I tell you this, then you believe me. So why do you believe me? And in which cases can it be that I argue something and my argumentation is buggy, but you don't recognize it? So this is very dangerous to argue, and we will see some examples today which you probably know from your everyday life. And sometimes you are angry about it, that people do this, either by accident or on purpose. And what I would like to tell you with these examples that we bring now is that natural language is not suited to use in computer science or in mathematics because it is not precise. So this argumentation is okay, but there are others which are not. And already Aristotle has thought about which flaws are there in the natural language argumentation which people can make use of to derive from two statements something which is not true, or from which you do not know if they are true, but you do not recognize it in the argumentation. And he identified certain types of such flows. We will just look at some of them. You do not need to remember these types. This should just give you the impression that the natural language is not suited to formalize mathematical facts, or also for secure argumentation. So the first one is, we can mention, is amphibology, and it is just an ambiguous grammatical sentence in a sentence. Structure in a sentence. So what do I mean with that? The best is to give an example. Teenagers shouldn't be allowed to drive. It's getting too dangerous on the streets. So actually the second sentence is the fact, and from that I derive the first one. It's getting too dangerous on the streets. So what is the relation of the two sentences? What do they have to do with each other? Teenagers shouldn't be allowed to drive because? What do I want to tell you? If they do, it is getting dangerous. That means they cannot drive secure enough. Or, yeah, it is too dangerous, so the teenagers are in danger if they drive on the street, because the other ones drive too dangerous. So these sentences could be taken to mean either that the teenagers will be in danger or that they will cause danger. So already here the argumentation is anyhow a bit floppy, but you can see that it is not unique to decide what I want to say. So even the facts are not always clear from the natural language. Another example is a professor tells to the student on receiving a 50-page term paper, I shall waste no time reading it. What does it mean? Yeah. So the student stays there and doesn't know what to do. So either the professor will avoid all delays to reading because he's so excited about this work, or he says that he will not misspend his time by reading it. And the last example, no food is better than our food. Okay, it's clear. So either our food is so good that you will not find any better one, or our food is so bad that it is better to do not eat anything. So these are really some examples where you can mean the opposite by the same sentence. Another type of fallacies are the fallacy of composition. This arises if you infer that something is true of the whole from the fact that it is true of some part of the whole. That means you have something, an object, it consists of smaller pieces, and you know that the pieces have some properties, and from that you infer that the whole thing should have some properties. Actually, this is true, for example, for sets of numbers. If you prove that something is true for one number, then you know that this holds for all numbers. But also there is this small mistake. Then if the number of numbers is infinite or even uncountable, then you can infer something from the pieces to the whole which is not true anymore. This is if you get from one order to the next order, for example, from first order to second order. But if we look at an example now not from mathematics, but also from natural language, you know that human cells are invisible to the naked eye because they are so small. So now you also know that humans are made up of human cells. And then if you make this mistake of composition, then you can also derive that the human body is not visible because each small piece is invisible, so then also the composition should be invisible. And this is, of course, not true. The other direction is the fallacy of division. Now, the other way around, you know that something holds for the whole, and then from this you derive something for the parts of which the whole consists of. For example, a typical mistake in science that was made in the Greek philosophy is that they assumed that if you have a material and this material has some properties, then also all of its pieces will have some properties. For example, if you have water, then the water consists of atoms. And if the atom is wet, then also if the water is wet, then also the atoms of the water should be wet. Or if you have iron, then the iron is hard, so also the atoms of the iron are harder than, for example, the atoms of the water. Or that the atoms of the wool are soft, and these things. So you can not, and this is not trivial to see, because if I tell you something, I have a set, I show you that something holds for this set, then I argue then also for the pieces this should hold. Or the other way around. If I use it in the natural language, you even do not recognize that there is a mistake in my argumentation. The next type of fallacy is the figure of speech. It is the use of words diverging from its usual meaning. Do you have some examples? This is something which you use a lot of times each day, and everybody knows what you mean. But, for example, if a foreigner comes that does not know your language and this figure of speech. This expression is not known in his or her own language. Mother language, then perhaps she will misunderstood you. I have one example for you. I had butterflies in my stomach. And of course, I do not really mean that I had butterflies in my stomach. Actually, I could. Yeah, but if I tell it to you, then it is not the thing that you assume. And this meaning is not fixed. So actually, perhaps I ate butterflies. There are some countries where you eat also insects, and this is, yeah, it could be, but probably I do not mean that. So also this is unambiguous. Then the next very typical mistake in natural languages is, I assume, or it is the fact that if P holds, then Q holds. And then now I know that Q holds, and I follow that therefore P must hold. Of course, in the logic that you get known, it is the other way around. If you know that P holds, then Q must hold. If you know that P is false, then you do not know anything about Q. But what happens if you go to the doctor? What does he ask you? Yeah, you go in, what does the doctor ask? So, what is this argumentation? I go to the doctor and he asks what I have, how I feel. I tell him my symptoms. And from my symptoms, he tells me my disease. What is the fact? What does the doctor learn during the studies? It learns that there are some diseases, learns the kind of diseases, and for each disease, there is a set of symptoms. The more symptoms, the more probable that this disease is due, these symptoms are due to this given disease. Okay, and I go to the doctor and I tell him I have, so what we know is that if I have the flu, then I have a sore throat. I have a sore throat, and I go to the doctor and I tell him this fact. And he says, okay, you have the flu. Is it true? You don't know. This is a kind of experience value. It can also be that it comes from another disease, which also can have this symptom. But the doctor must choose one, so that's why also it is not the fault of the doctor. Actually, he takes the most probable choice. But you cannot derive from the symptoms the disease. Perhaps you can measure some blood values, and then you can prove that this is indeed this disease. Even then not, because there could be another disease the doctor didn't think about which could have the same properties. So, of course, it helps me if I really have the flu, that the doctor made this implication backwards. But you cannot rely on it if you want to go for soundness. Yeah, because this implication could be wrong and he could derive something which is false, because I do not have the flu. Okay, another category is irrelevant conclusion. This is the informal fallacy of presenting an argument that may in itself be valid, but does not address the issue in question. This is very popular in politics. So, for example, I could say, I think that we should make the academic requirements stricter for students. I recommend that you support this because we are in a budget crisis and we do not want our salaries affected. And I listen to it and say, oh, my salary. Don't take my money away. So if I am not sharp enough and think about this irrelevant conclusion, then I could say, okay, I support you. And if it is, this is now in this example very extreme, you can recognize it, but sometimes in a discussion people do not recognize it, and then they believe you, you believe them, though the argumentation is not correct. So there is an irrelevant conclusion. This is also called red herring, and it is typically a debating tactic. Okay, and I think the last one that we look at is the questionable cause. These are also informal fallacies where a cause is incorrectly identified. So an example, HDL, this is a cholesterol type, and this is called a good cholesterol because it is negatively correlated with incidence of heart attack. This is just a statistical value. And now, for this reason, if we take medication to raise HDL, then it will decrease the chance of having a heart attack. Is it true? Do you believe me? Yeah, so if your HDL would be low, would you take this medicine to increase this level? Would you expect that the probability to get a heart attack would be lower? You say no? Exactly. So I do not know if this is how it is related. I don't know only a statistical value. So it can be that, and actually the fact is that the genes affect both. They affect both the HDL level and the likelihood of getting a heart attack. And if I modify one, this will not modify my genes. So it will not have any effect on the probability to get a heart attack. But since there is a correlation, it is not clear if it indeed, if I increase one, then the other one will be, in this case, negatively lowered. And in medicine, from these statistical measurements, people try to treat people if there are no other ways. So either it works or not, because the argumentation is not logically correct. There are also some other, I have two more examples. With a decrease in the number of pirates, there has been an increase in global warming over the same period. Therefore, global warming is caused by a lack of pirates. You laugh because this example is more extreme, and of course you would say, this is not true, and then you would search for where is the mistake, and this is this questionable cause. But this was not so clear in the first example. So you can really hide it, that it is not trivial to see. And another nice example is more and more young people are attending high schools and colleges today than ever before. Yet the rate of youth crime is also much higher than in earlier times. This makes it clear that these young people are being corrupted by their education. And if people bring these arguments and the humans do not take care, then indeed you can get such proofs of education is wrong. Good. So now we had some fallacies. First, inambiguities or wrong argumentation. And besides these, a big problem with the natural language is that you can talk about the language itself. The natural language is so powerful that it is far beyond undecidable. I mean, it even doesn't have perhaps it has a formal syntax because you have grammar, but it is also dynamic. It changes with the time. So it is not fixed, but the semantics is far beyond fixed. So you cannot define it precisely. You cannot put it into a framework, formal framework. But beside this, it is so expressive that it can talk about itself, and every time, if you have a logical system where you can argue, and this system can talk about itself, then this is the boundary to undecidability. So I assume that all of them know that there are problem classes for logics which are undecidable. The halting problem should be known to all of you. And in the natural language, this undecidability becomes visible by different points. For example, sentences which are paradoxes. So the natural language does not satisfy the requirement of being conflict-free. Yeah, because I can derive, or I cannot decide for each statement if it is true or false. This is incompleteness, but worse, I can sometimes derive none of them or both. So what is with this sentence? The liar's paradox says this sentence is a lie. So is this sentence true or false, or can it be both? It's true because it's false because it's both. Actually, it's a paradox, so none of them. Yeah, you see, if this sentence is true, then this should be a lie. So it should be wrong or false. And if I assume that this sentence is false, then it is not a lie. That means this should be true. So I can tell sentences which are conflicting in themselves. And another property is, so it is inconsistent. And another property is that the language is so expressive that some properties which I extract from a logic are not true anymore. In logic, you assume if I have one property and I have another property, and I take the conjunction of them, then the conjunction is also true. For example, I say the sun is shining today, and we are now in the satisfiability checking lecture. Now I make the conjunction. The sun is shining today, and we are now in the satisfiability checking lecture. If both are true, then also the conjunction is true. This is not true anymore if I talk about the language itself. For example, I put the sentence, this sentence has 5 words. And if you count, this is true. And now I make the conjunction. This sentence has 5 words, and this sentence has 5 words. And now I put them together. I talk about words in a sentence, so the conjunction does not have this property that two sentences put together by conjunction keep the truth value. Did anybody of you read the book Gödel, Escher, Bach? Yeah, this sentence, I took that from this book. This is really very nice. He discusses this undecidability problem and this natural language properties in a very nice way. So it is really nice to read it. If you have some time, then it combines actually kind of computer science and art and music. That's why Gödel, Escher, Bach is the title. So now we know that the natural languages are not well suited for secure argumentation. And of course also the philosophers came to this conclusion. We have seen now Aristotle's observations, and then people started to try to put it on a formal way. And this was a very long way. If you get now today this crystal clear and clean result, for example, of propositional logic, then you say, okay, I understand it. But the way from getting argumentation in the natural languages till propositional logic, which you also call Boolean logic, was very long, because mathematics was not so far developed that you have this, what you already learn in ground school here. This was a long way. So this went from the mid of the 19th century, actually till the mid of the 20th century. And I do not go now deep into it, but some milestones. So in 1854, George Boole, and from his name Boole, come to the name Boolean logic, he introduced some symbolic logic. That means from the language with words and sentences, he tried to use new symbols with fixed meaning and tried to combine them with fixed operators. So he introduced symbolic logic and the principle on what is now known as Boolean logic. So you have propositions and you have conjunction and negation. At that time, no quantifiers yet. That came later. Gottlob Frege, kind of 20 years later, created his Begriffsschrift. And in this Begriffsschrift, he extended a kind of Boole's work in that he introduced quantifiers. And this was a very big step. So now with the quantifiers and the Boolean variables or propositions and the operators, we have what is the simplest first-order theory. And it took quite some time till this was lived up to the numbers. In mathematics, Whitehead and Roussel published the Principia Mathematica. Probably you heard about it either in math or in other lectures. This is the basic foundations of mathematics, and what they tried in this work, they attempted to derive mathematical truths from axioms and inference rules in symbolic logic. That means now, until now, there was only a kind of argumenting about the numbers, and they tried to axiomatize what is a number and what are the operations that I execute on these numbers. And this is more complex than you think. If you have never got known to the axiomatization of, for example, the real numbers with addition and multiplication. And this is a decidable logic. This is called real algebra. And it is non-trivial how to axiomatize it in a way that you can argue. First, it should be minimal, and this should be free of contradictions, of course sound. And since this is a decidable logic, this should be complete. And optimally, this should be finite, because otherwise you cannot derive any complete decision procedures from it. We will look at it later, not now, but after the first third of the semester, just to have some fun, because this is really, really very nice. How you can, also this historical development. So we will look at it later, not in depth. We will not go deep into the mathematics, but some interesting aspects. So now there was a mathematics which was axiomatized. And this was unique, what we mean if I write down a mathematical statement. And this was fine, and this was around 1900. And then the mathematicians, the 19th century was really very fruitful for mathematics. A lot of new things were developed, and people had the impression now they understand everything. And then at the change of the century, the mathematicians made a congress, and they invited Hilbert to give a speech, and they expected that Hilbert will talk about the great achievements of the last century. And Hilbert did not do this, but he stated 23 unsolved mathematical problems. And 2 of them were devoted to, that's what we deal with in this lecture, are the logic that we use in mathematics. And now the question was devoted to the natural numbers. So actually, integer arithmetic, what we learn in school, we have natural numbers, we can have variables which have natural values or integer values. I have addition and multiplication. This is basically the thing, integer arithmetic. So it seems not complicated. And now we have an axiomatic system, but what we did not answer yet are these 3 important properties that we discussed. Being free of conflicts, not being consistent. Soundness, that means I can derive only true facts. And completeness, that means from every fact, from every problem, I can decide if it is true or not. And this, everybody expected that this holds. Yeah, now they have this axiomatic system which seems to be well suited now. It was only the last step of doing the proof that these three properties hold. And then it took about 30 years. Everybody went and tried to solve these problems. And also a lot of people tried to solve this actually final decidability results. And then Gödel and Turing, Gödel was the first, Turing a bit later, from two different aspects they answered this question, but not positively but negatively. So they showed that the theory of the integer numbers, of the natural numbers, with addition and multiplication are too strong to be decidable. That means there are problems for which there is no answer. Or with other words, there exists no decision procedure which would take any formula from this logic and it would give you the answer, just because these answers do not always exist. And now if you already know the halting problem, then you know that there are undecidable logic. But imagine for those people, there were some mathematical problems and people were so fascinated that they devoted their whole life in trying to find an answer, a proof for something, which was a conjecture. And then these two guys come with some undecidability results and tell them, okay, perhaps you wasted your life because perhaps there is no answer to this question. So this changed really a lot. And now if you go back one step further to computer science, what is for us important is which logic is decidable, or if you have a certain problem, you want to solve it. Is it a decidable problem? Because if it is decidable, if it stems from a decidable logic, then you can use the computer to solve it. Then there is an algorithm that if you program this algorithm, then you just plug in instances, problems from this logic, and it will give you the answer automatically. So that's what we can do in computer science. If it is undecidable, then you can still define some incomplete algorithms, which, if you have luck, give you the answer. But still then, you expect that your algorithm is sound. That means if it gives you an answer, then this answer should be correct. And if your logic would be inconsistent, then you could forget about it. Then it does not make any sense. So these three properties you got already known during your computer science studies. And now the question is, actually a lot of problems for which you try to find solutions and develop in different lectures can be led back to some mathematical logic. And now in this lecture we will determine certain logics, which are the most typical ones, perhaps also some which is related to programs, and we will look which of them are decidable. If they are decidable, then how could a decision procedure, that means such an algorithm, look like? And if I want to implement it, that means to get the answers automatically, what do I have to take care about? What is important for efficiency? And also efficiency is an important word. You probably also already listened to complexity. Theory is related to undecidability, Berechenbarkeit und Komplexität. And what we want to have is efficient, and if I mean efficient, it has two meanings. They are mixed. The first meaning of efficient is polynomial. And polynomial is, we say, good. If the size of the problem grows, then the time or space for solution grows only polynomially. This is still very fast, but this is something which we can hope, because this is even only for the worst case, we can hope that I still can solve larger problems. That means my method scales, we say. However, there are also other problems which belong to the non-polynomial class. And since we do not know if P equals NP, we do not know if there's polynomial solution, but we can prove that some problems belong to that class. At least this is an upper bound, and we do not have any better ones until now. And then if something is exponential, then if the input size grows, then the solution time grows so fast that the scalability is not given anymore. And then we will look, perhaps, can we define some incomplete algorithms which work more efficiently on a sublogic, on a subpart, can we combine them, and so. Yeah. And then, of course, we are now in logic in computer science, and the logics which we will look at, you already used during your studies in school, and we also use later. So where do you use logic in computer science? In which areas did you already use logic in the lectures or? Model checking, for example, so verification. Verification is a very typical example where you use different logics depending on the kind of the system. Perhaps some areas of computer science where you have logic. Digital logic, circuits. This is first to the logic without any theories behind. So for that you need proposition logic, and you can use it for specification or also for verification. And indeed, such solvers, which we will look first at. We will look first at proposition logic, and the such checking is the decision procedure which is used to solve such formulas, is massively used in industry for circuit verification, or at least for bug hunting. So they have their own Abteilung, own group of developing such solvers for their special circuits which they develop. Some more examples? Yeah, typical. They have even different kind of logic. They have also something we will not like. We will not look at this fuzzy logic, for example, or this, what is this logic about beliefs? But nevertheless, they also use formal logics. Some other areas? What is about databases? What do you use there? What is a query language? Now to specify something by a formula. Yeah, telling that, I don't know, in this kind of property you have a certain entry in this table, and in another table, I do not know, you relate these properties and write down a formula in a query language. And what do? If you do first search or generate new table, this formula will be evaluated. You get its semantical value. This is also a logic. So there are logics which you do not, they do not look like logic at the first sight, but there are some. So some further programming languages. This is typical. A programming language is a logic. Yeah, what do? You write a program, and then you execute it. By executing it, it will be evaluated. Of course, perhaps the evaluation is not complete because the program doesn't terminate, so this logic is undecidable. Sometimes the output is not the answer, what the program returns does not exist, or if you define as a meaning of the program not only the return value but perhaps also the value non-terminating, then in general you cannot decide which value this program has. But, for example, if the program terminates, then you get its value. This is its output. So you have a formal syntax, you have a formal semantics. So this is a logic in the widest meaning. And we had also verification or specification. So logical is very important in a lot of areas of computer science. And now what we will look in this lecture is first propositional logic and first order logic with different theories. What we will do not look is higher order logic. So what is the difference between first order logic and higher order logic? Let's say first order logic and second order logic. Long time ago. Exactly. So in first order logic, you quantify over elements. In second order logic, you quantify over sets. In third order logic, you would quantify over sets of sets, intuitively. And most logic, if you have higher order, they get undecidable. And what you also do not look at is temporal logic. This is arguing about passes of transition systems, for example, program execution. In temporal logic, you have operators like for all passes something holds, or there exists a path that something holds until another property gets valid. We will not look at them, we will concentrate on first propositional logic. What is propositional logic? If you should tell me, how can I build a propositional logic formula? This everybody of you should know, actually. What can I use to build such formulas? Predicates is the atomic part, and how can I build up other propositional logic formulas from predicates? Conjunction and conjunction alone is a bit weak. Negation. And from these two, I can express all other Boolean operators that you know, like disjunction or implication, if and only if, XOR, not and so on. Everything that you also know from circuits. So first we will look at propositional logic, and as I said, we will look at fuzz solving. Of course, if I give you a formula, then you can check it for satisfiability with already methods which you already got known to, like truth tables. Yeah, everybody can do that. I have n variables, I have 2 to the n possibilities, and you can check them through. But this is exponential. Actually, the problem is NP hard. So we will try to find better ways, which in worst case, of course, also are exponential, because the program class is so hard, but in most of the practical cases it works most efficiently, and this allows to apply these techniques in practice. Then we will extend this logic, and we'll talk about general first-order logic, and then we plug in some certain theories. And one theory is the theory of equalities. That means I have basically the same like in propositional logic, but now the variables may have different domains. And the only thing what I can state is if two things are equal or not. And this helps me already a lot. This is not more expressive than propositional logic, as we will see, but it eases the modeling. It eases the specification if I want to talk about problems. And if I extend it even with uninterpreted functions, then this is the logic which is for which solvers exist, which are pretty fast. That means they are used in practice very often. With these uninterpreted functions, what are these? What are functions? What is a function? Okay, so I have a function, usually we write this one. I have a domain A. I take elements from this domain and I assign some elements from another domain B. And the interpretation of this function gives its meaning. For example, I can say for all x, f of x equals, let's say this is r, the function from r to r, f of x equals 2x. That means each value I assign the double. And now an uninterpreted function is if I do not fix this meaning. What I still know is that it is a function. And as a function, the only thing what remains, what I still know, is that if I put in a value twice, then I get out the same result. That means if I know that x, I think it's even written here, if I know, this is not directly what I wanted to write, so I write it here. If I know that x equals y, then I also know that the function value of x equals the function value of y. This is congruence, and this defines a function. If this does not hold, then f is not a function. Then it could be at most a relation. So uninterpreted functions is where I do not tell anything about the meaning of the function, but I tell that it is a function, and thereby I can build a kind of black boxes. Yeah? If I have a complex system and I do not want to specify one part because I assume that this part is not relevant for my property, for example, what I want to verify, then I just tell, okay, this block works as a function. I do not know what it does, and I hope that it is not relevant. So just assume that this is an uninterpreted function. And that's why it is used very frequently also in industry, this logic, equality with uninterpreted functions, because it is expressive enough to tell properties of a system, and if this is not enough, that it is the functions are uninterpreted, then I can add properties stepwise. And then I can refine my statement until it is strong enough to be proven or disproven. Okay, and if we are done with that, then we arrive at the numbers, and what we deal with is real and integer numbers. Actually, until here, this is, let's say 1/3 of the semester or a bit more. And then we will come to the numbers, first linear. Linear arithmetic is what we deal with mainly. And probably some of you already know the simplex algorithm. Yeah? This is for checking linear real arithmetic constraints for satisfiability. We will look also at that. We will even look at something which is an extension of SAT solving that is called SAT modulo series solving, SMP solving. And we will look at how we can plug in those theory decision procedures into this more general framework where you have also Boolean combinations of. For example, simplex you can only take for the conjunction of linear constraints. And if you have also Boolean combination, then you can use a kind of SAT solving to check the Boolean skeleton, the Boolean structure, and then simplex for the real arithmetic part. And we will also look what happens if we have integers. So assume I have such a formula, 2x plus y larger than 0 and x plus y is less or equal than 0. In general, we want to ask the question, is this formula satisfiable? So is it satisfiable? What do you say? Exactly. So for each y, there exists another x which compensates it if it is large enough, positive and large enough to compensate the value of y. And now if I put something like 2x equals 1, is it satisfiable? Exactly. And this is the main difference. In real arithmetic, I just have to, basically real arithmetic, linear and nonlinear are both decidable. That means if I have real-valued variables with addition and multiplication, then I can give an algorithm. You give any formulas from this logic, then this algorithm gives you the answer if there is a variation for the variables, making the formula true. If I go to integer arithmetic, then it changes in that I do not need only a solution, but this solution must be integer. On the one hand, the intuition perhaps tells us, yeah, integer, this is easier because there are less numbers. But if we go to nonlinear arithmetic, that means we have also multiplication, then real algebra, the reals with addition and multiplication is still decidable, but for the integers, this is not the case anymore. So the integers with addition and multiplication is undecidable, and we will not deal with them. So basically the main lecture will stop here, and by real algebra, and not quite by real algebra, we will look at least to one incomplete decision procedure, because it is very nice algorithmic, and we will look some other complete only at the intuitive niveau. So we will not go deep into math, but this is a really very fascinating area. So the main part is here. We will learn different decision procedures for these logics, and then we will do also something for here, but only for the real. So real algebra is basically formulas over polynomial constraints. So, and actually that's all what I wanted to tell today. Do you have any questions? No. Then on Thursday we will have 2 hours lecture, and we will start with proposition logic first, formalizing syntax and semantics. Thank you.